Hello and welcome to this new tutorial. Now we're going to make that method that creates the VAE model architecture itself and also the method that will integrate the training operations. So let's do this. You already know the name of that method because we already called it actually. It's exactly this method, so I'm going to copy this because in order to introduce a method here, we need to start with def to define the method and then just give the name of the method, which will be build graph. However, inside we have to specify the argument self because we're going to use, of course, the variables of our object, and no other argument is needed here. And therefore, we're already ready to start implementing the build graph method. And the first thing we're going to do before, making the whole architecture of the convolutional variational autoencoder is to initiate the graph, because the VAE will be constructed as a TensorFlow graph, and therefore now what we're about to do is create an object of the graph class by TensorFlow, so that our VAE model gets the dynamic graph advanced structure, which will be super useful when it is time to train the VAE model, right? The dynamic graphs are a great innovation in the AI platforms. You also have them in PyTorch, and basically they allow faster computations of the gradients, and more specifically the gradients of composition functions in the training computation. So that's a must do. We have to start here by creating this graph, and therefore I'm introducing a new object variable which will be self.g. So g will be the graph itself, and to create this graph, as we've just said, we're going to create it as an object of the graph class by TensorFlow. So I'm calling TensorFlow, and from TensorFlow I'm calling the graph class. Here it is, and we just need to add some parentheses because this is indeed a class. Alright, and no argument is needed in the class. You have your graph ready. It's basically initialized, and later on it will be used inside the TensorFlow sessions that will run for either the inference or the training. Alright, so here we go. We have our graph. That was the first step. And now the second step is to specify that we want to have the whole architecture of the VAE model that we're about to build inside the graph. And therefore, in order to specify that we want to integrate indeed this architecture inside the graph, we have to start with width here and set the graph, which we called self.g, as default, right? The first one here. Then let's not forget some parentheses, and then colon. And then as you can see, when you press enter, we are inside this graph set as default, right? That's where we're going to build the whole architecture of the VAE model, inside this graph. And so here we go. We're ready to start. And so now what we're going to do is go back to the appendix section of the World Models article written by the original authors, because indeed, as we saw in the previous tutorials, it contains the full architecture, the exact same one as the one we're about to build. And so what we're going to do is simply follow this architecture from the top to the bottom, because indeed we have to start here with the input images, and we're simply going to follow the architecture with the same numbers here of input tensors, meaning feature maps here and elements in the latent vector, and then input tensors in the deconvolutions. So let's start with the very top, the first step here, which is to get the input image with the following dimensions: 64 by 64 by 3. And 64 by 64 are basically the height and the width of the images. They're going to be squares of 64 pixels. Alright, so that's the first thing we're going to do here. And the way we're going to do this is by first introducing a variable that we're going to call x, and which of course will be a variable of the object. And this x variable will be exactly the input images of 64 by 64 by 3 dimensions. And so we're going to create them inside a TensorFlow placeholder. That's usually the way we do things when dealing with images, because this TensorFlow placeholder will create the right format for these input images with the right dimensions. And the way we're going to do this is by first, of course, calling TensorFlow, which has a shortcut TF. Then from TensorFlow, we're going to call, as we've just mentioned, the placeholder function, inside which we are going to input its arguments. And the first one is D type, meaning the type of the elements that you'll have in the cells of the arrays, which are of course going to be the pixels of the images. And of course, since we're going to normalize the pixels, which originally are between 0 and 255, but after normalization there will be basically floats. So we have to specify the type of the cells as floats, and the way we do that with TensorFlow is by calling TensorFlow, and from TensorFlow we get the float 32 type. Alright, so that was for the first argument, and then I don't know if you saw, but the second argument is actually the shape of the images. And as we saw, well, we can see that again, the shape of the images are going to be exactly 64 by 64 by 3. Alright, and that's exactly what we have to specify in the second argument here, in brackets, inside which we have to input 4 elements. The first one is the dimension of the batch, in case we want to specify that we want our placeholder holding the input images inside batches already, but no, we won't get them into some batches yet. That's not right now that we do this, we will do that later, and therefore we will specify none as the first element. And then, of course, the 3 other elements are the dimensions of the images. And therefore, as we've just seen, they are 64 for the first one, 64 for the second one, and 3 because we are working with RGB colored images as opposed to black and white images, in which case the dimension would have been here 1. Alright, here we go. We took care of the input images, meaning we took care of the first step here, input image 64 by 64 by 3. And now we're going to tackle the first part of the VAE, meaning the part where we build the encoder, right? You have to understand that we're going to build this convolutional VAE model in 3 main parts. The first part is going to be the encoder. That's the encoder, encoding the input images into the latent vector. And speaking of the latent vector, that's actually the second part of the implementation of the VAE. And then the third part, which is of course the decoder, right? Here we are decoding the latent vector Z to reconstruct the final output, that is the final output images, which are going to be the representation of the environment inside the dream. So, of course, I'm going to structure our code now in these 3 parts, starting with the first one, which will be building the encoder part of the VAE, variational autoencoder. And so now here we go. Let's build exactly the same architecture as we see here. Starting with the first convolution, a ReLU convolution, meaning it's going to be a convolutional layer of 32 times 4 feature maps with a ReLU, meaning a rectifier activation function. And this is exactly what we're about to implement right now. You'll see that we will only add 1 additional info that is not here, which will be the stride, but the stride you will see is most of the time 2. That's why they didn't specify it here. Alright, so let's do this. It's actually very easy with TensorFlow. We're going to call our successive layers of the encoder and also the decoder, by the way, H, because they're like hidden layers. Here we go, H. And so now to create these convolutional layers, well, you might guess that the first natural step is to call TensorFlow. And then from TensorFlow, we're going to get a first module, which is very easy to remember because indeed right now we're creating some convolutional layers and therefore layers. That's the model of TensorFlow. And inside this layers module, we're going to get the conv2d function. And so here we go. We can see very well the arguments of the conv2d function, but I've prepared in the resources another one, which is not as important as the ones I've given you, but pretty useful for what we're about to do right now. It's the TF layers conv2d from the TensorFlow documentation. So how did I get that? I basically just typed layers conv2d TensorFlow on Google and I directly got it, right? That's how you can get easily and fast the information. And so this is useful because indeed you get all the detailed informations about the arguments of this conv2d function we're about to use to build our first convolutional layer. And so let's input these arguments one by one. The first one is input, and that's of course going to be our input images, which we created here. So we can just copy this and enter this as the first input of the conv2d function. Then let's see, the next argument is going to be the number of filters or the number of feature maps. That's the same thing, right? As you can see, the number of filters in the convolution, as you saw in the intuition lectures. And so now the question is, how many filters do we want right now? Well, the answer is in the architecture provided in the article, and that is 32. 32 feature maps or filters. All right, let's do this. Let's implement that. 32 filters, and now next argument. You can see how all this is pretty easy. Let's see what the next argument is. That's the kernel size, the size of the kernel which you saw in the intuition lectures. And again, the answer of what kernel size we want is here, right here. It is 4, right? 32 feature maps or 32 filters of size 4x4. That's what it means here. So let's do this. Let's go back to Python and let's input 4 here. And then what is going to be the next argument? Well, let's see here. All the answers are here on the several resources we have. The next argument is going to be the stride, which again you saw is by how many cells are shifted. The filters are 32 filters of size 4x4. And so as we've seen, the stride is not given here, but as I've told you, it's usually stride equal to. Then, next argument, let's have a look again at TensorFlow, the TensorFlow documentation. The next argument is, well, you have many of them. You have the padding, the data format, the dilation rate, the activation, and more of them. So no worries, we don't have to enter all of them. We're just going to keep their default values. However, we have to specify the activation function because we want to use the rectifier activation function. And as you can see, this is not the default value here. The default value is none. Therefore, we're going to specify this in the argument. And remember, in the world models, it specifies which activation function it uses for this first convolutional layer. And it is a ReLU activation function, or in other words, a rectifier activation function. So here we go. Let's implement it. As for strides, we have to specify the name of the argument because this is not the next one in the list of argument. So activation equals, and to get the rectifier activation function, we need to get it from TensorFlow, then from the NN module of TensorFlow, and from the NN module of TensorFlow, well, here we go, we get the ReLU function, activation function. All right, perfect. So now we have everything we need, but we're just going to add one final argument just to give a name to that specific convolutional layer, which is the first one, with the last argument that we can use here, which is simply the name, right? And so the name for this first convolutional layer, well, we can call it encoder with enc convolution conv1, the first convolutional layer of the encoder, because then we'll get also some convolutions or inverted convolutions, but for the decoder. Then no worries about the warning, it's only because we haven't used H yet. But we're about to use it right now because H, this first convolutional layer, is going to become the input of the second convolutional layer. So actually what we're going to do to be efficient in order to create that second convolutional layer is paste the first one. And then the first very important thing is not to forget to replace self.x, which was, of course, the input of the first convolutional layer, but the first convolutional layer only, because now the input tensor of the second convolutional layer is going to be the first one, h. And we can override h here, because what only matters to us is the final outcome after the convolution. So basically here, we're just applying the convolutions one after the other by inputting on the new one the previous one. And so I'm replacing the self.x here by h. And now the second thing that we need to do is check the architecture here. What we want for the number of feature maps or filters, and same, do we want the same size, the same stride, etc. So the answer to that question is again right here, and the architecture of the original variational autoencoder made by the authors. And as we can see, the second convolutional layer has 64 filters of size 4 by 4. So here we go. We're going to implement that right away by simply replacing the 32 here by 64, and we already have the right size of the filters. And then let's check if we have the same activation function, and yes, it is the same. It is the rectifier activation function once again, so nothing to change here. And here, of course, we're going to replace oncconv1 by oncconv2 because this is the second convolutional layer. And here we go. Now you're going to see how we're going to be so efficient at finishing the creation of this encoder, because for the next one, well, this time we don't even have to replace H here, because now this new convolutional layer is going to take as input the previous convolutional layer. So H here corresponds to that H here. And now let's have a look at the architecture to see what number of feature maps or filters we want for this third convolutional layer. And we want 128 filters of size 4 by 4. And we also want a rectifier activation function. So it's going to be very quick now. Basically what we only need to do is to replace 64 here by 128 and oncconv2 by oncconv3, the third convolutional layer. And then here we go again. I'm going to copy this new convolutional layer and paste it here. And now the fourth convolutional layer is going to get as a tensor input the previous convolutional layer, the third one. But this time this new convolutional layer is going to get, well, you might guess that it's going to get the double of 128. Indeed, ReLU-conv 256 filters of size 4 by 4. So here we go. Here we only have to replace 128 by 256, then of size 4 by 4. And again, we have a rectifier activation function to let the signal pass inside the convolutional neural network. All right, and let's not forget to replace oncconv3 by oncconv4. And here we go. We have our fourth convolutional layer. And does that mean that we have everything? Yes, we do have everything. We are ready for the next step of the creation of this variational autoencoder, which is to flatten the result of all these convolutions here that happened into a one-dimensional vector of 2 times 2 times 256 elements. And so the way we're going to do this is actually very simple with TensorFlow, because, you know, I already did that with some other AI platforms and I actually had to make a function. But here, the way we can do this very easily, as TensorFlow allows us to do, because indeed to flatten the result of these 4 convolutions, well, the only thing that we have to do is get, of course, first TensorFlow, and then from TensorFlow we're going to get the reshape function. And the trick to reshape the result of convolutions inside a one-dimensional vector is simply to input first, as you can see, the final tensor that you got as a result of the 4 convolutions here, which is of course H. So here we go, H. And then, as you can see, the next argument is the shape, which you have to enter in square brackets, inside which you're going to input 2 elements. The first one is -1 to say that you want a one-dimensional vertical vector. And then, of course, the second argument is going to be this exact same number here, 2 times 2 times 256. And that's, of course, the number of elements you want to have in this flattened vector. So here we go. That's the second element here, 2 times 2 times 256. And congratulations, you are done with the first part of the creation of this VAE model. The encoder part is done. So now we're going to move on to the second part, which is going to be the V part of the VAE model, to sample stochastically the latent vector Z from a Gaussian distribution of mean mu and variance sigma. So let's do that in the next tutorial, and until then, enjoy AI.